Today we are going to discuss about the electronic configuration, how to write an electronic configuration. So first of all, what is electronic configuration? An electronic configuration is basically the distribution of electrons in a given set of orbitals in an atom. So leaving apart hydrogen, which is a uni-electron atom, all other atoms are multi-electrons. So there are many electrons in an atom. So all those will be distributed in the given set of orbitals in an atom. So how to arrange those electrons in that orbitals is governed by three different principles, which I will be discussing here, and which are the guiding principle of distributing electron and in the various orbitals in an atom. So the first principle is called Pauli's exclusion principle. So the word here is exclusion. So in our previous lecture, we discussed about the quantum numbers, and we discussed there are 4 quantum numbers. So according to Pauli's exclusion principle, no two electron in an atom can have same values for all the 4 quantum numbers. So take any atom, and if you have 2 electrons in that atom, it cannot have the same values for all the 4 quantum numbers. It can have the same values for the 3 quantum numbers, but it cannot have the 4th value same for the quantum number. So one of the quantum number will have a different value for each of the electron present in an atom. So what we can infer from the Pauli's exclusion principle is that an orbital can have a maximum of 2 electrons. It cannot have more than 2 electrons. So that's period. And the word exclusion is that out of 4 quantum number, 1 quantum number is excluded, and that's what I meant by that no 2 electrons can have the same values for all the 4 quantum numbers. The second principle which guides the distribution of electron in orbitals is the F-Boy principle. According to the F-Boy principle, when we are distributing electron in a given set of orbitals, the electrons go to the lower energy orbital first. So the orbital which has less energy associated with it, the electron is going to go into it rather than the orbital which has higher energy associated with it. So the electron goes to the lower energy orbital first. So that's the second guiding principle for distributing electron in orbitals. The third principle is called the Hund's rule, and if I can extend it, it's called Hund's rule of maximum multiplicity. I won't go into that detail why it's called maximum multiplicity. So according to this rule, in degenerate orbitals, so the word here is degenerate. What is degenerate? Degenerate means the orbitals having same energy. So we are talking about not the orbitals not of different energy, we are talking about orbitals which have same energy. So in a set of orbitals which are degenerate, means having same energy, electron pairing will not take place until each orbital is singly filled. So as I said, that an orbital can have a maximum of 2 electrons. So the pairing, the second electron will only enter into that orbital once all the orbitals of same energy are singly filled, means they have at least 1 electron in it. So that's the Hund's rule. So these 3 principles will be a guiding principle for the guiding principles for us to distribute electron in a given set of orbitals. Okay. So for writing the electronic configuration, as I said, there are 3 principles which are going to guide us, and in order to just make it more convenient to write down the electronic configuration, I'll refer to this diagram here. This is a kind of an energy level diagram which depicts the various shell, subshell, and the orbitals. You may take that in that form in increasing order of their energy. So it starts from the 1s subshell. So in the first shell, there is only one subshell, which is S, so which is the lowest most energy. And as you move up, the energy goes on increasing, And if you remember the F-boy principle, it states that the electron will go to the lowest energy orbital first. So if an atom has just one electron, it will go to the 1s orbital here, okay. And then the Pauli's exclusion principle, which states that there can be a maximum of 2 electrons in an orbital. So in 1s subshell, there is only one orbital, so a 1s subshell can have a maximum of 2 electrons. Okay, so we can only have 2 electrons in the 1s subshell. Now suppose there are 3 electrons in an atom. We'll take those examples. The third electron will go into the 2s subshell. Then if there are 4 and so forth. So for the guiding principle, that how we are going to determine that in which orbital the electron will go, will refer this diagram, and it's very easy to draw. You can say 1, 2, 3, 4, 5, 6, and then you draw the other. So in 1s there is in one first shell there is only one subshell S. In the second shell there are 2 subshell S and P. Remember, for n is equal to 2, the L value is 0 and 1. For n is equal to 3, the L values which are possible is 0, 1 and 2. For n is equal to 4, the various L value which are possible is 0, 1, 2 and 3, and so on and so forth. So this diagram is according to those 4 quantum numbers. So I'll draw what you call the arrows which are going to determine the various. Okay, so after drawing that diagram containing the subshell, what I did here is I just draw the diagonal lines. So these diagonal lines represents the order in which the electrons will be filled. So I'll start from the bottom part here. So the first 2 electrons will go in the 1s. The third electron and the fourth electron will go in the 2s subshell. The 5th onward till the 10th will go into 2p, and once the 2p is completely filled, then the electron will go into the 3s. Once the 3s is completely filled, the electron will go into the 3p subshell. Once 3p is completely filled, the electron will go into the 4s subshell. So that's very important. The electron is not going into the 3d subshell. So once 3p is completely filled, the electron is going into the 4s subshell, and that's one of the reason it says is because the 4s subshell has lesser energy than compared to the 3d subshell. So once 4s is completely filled, the electrons will go into the 3d subshell, and once that is completely filled, it will go into the 4p and so on and so forth. So this diagram here is a guiding diagram for us to assign electrons in various orbitals based upon the 3 guiding principles which we talked about. So let's take some example and write down the electronic configuration. So let's take the first atom in the periodic table, the atom which has only 1 electron and 1 proton associated with it. So I can write the symbol of hydrogen as such. So in this case, when I am writing 1 and 1, what does that represent? That it has an atomic number of 1, and it also has an atomic mass of, or the mass number 1. So it has 1 electron and 1 proton. So this is what it depicts. So based upon the atomic number here, I can write down the electronic configuration. From the atomic number, I can know how many electrons are there in an atom. So its atomic number is 1, so I can say there is only 1 electron in an hydrogen. Now where that electron will go? So this is the diagram. The hydrogen has only 1 electron in it, and where it will go? So I'll give you just a couple of seconds to think. You're right, this electron will go in the 1s subshell. So I am going to depict here each orbital in the form of a box. Okay, so this box here represents a 1s subshell, and to the matter of fact, since it's an s subshell, it has only one orbital. I can say this is 1s orbital, and since hydrogen has only one electron, and that electron will go into the 1s subshell. So I have shown electron in the form of an arrow, and I have shown it in an upward direction. By convention, it is say that this electron has a clockwise is spinning in a clockwise direction. So what I can say as far as the various quantum number value associated with this electronic configuration is the electron is present in the first shell, the subshell is S, so L is 0, and for L is 0, there is only one ml value possible, which is 0, and since I have shown this arrow upward, I can say the spin quantum number will have a value of plus half. You may ask why it's not facing downward. It's just a convention, it's just the way it is represented. You can show it down, it won't be wrong. The only thing is it will be negative half. So this is the quantum number. I've given you information about the quantum number associated with an electronic configuration. So when you see this, I can simply write the electronic configuration of hydrogen as 1s1. I can write on the sidewise also. The electronic configuration of hydrogen is 1s1. Electron present in the first shell, electron present in the s subshell and s orbital, and there is only one electron in that. So this is the electronic configuration for hydrogen. As far as helium is concerned, the atomic number for helium is 2. So that means there are 2 electrons in an helium atom. So how they are arranged? So again, I'm going to show it in the form of a box, and this box represents the 1s subshell, just like here. In 1s subshell, there is only one orbital, and an orbital can have a maximum of 2 electrons, So the first electron will go into the 1s subshell. Where the second electron will go? The second electron will also go into the 1s subshell. Now here will be the catch. Whether the second electron will have, can I show it in this fashion? Means both having the upward spin, or whether it should be in some other direction facing downward. And I want to concentrate here, I want all of you to concentrate here on the Pauli's exclusion principle. Now the Pauli's exclusion principle says that no 2 electron in an atom can have the same values for all the 4 quantum numbers. Let's see whether that principle is followed in this case of an electronic configuration. Let's see that. Let's write the electronic configuration for the first electron. So N is 1 because it's present in the first shell. That's what the information I get. The L value is 0 from the S. So, and when L is 0, ML can have only one value, which is 0. And since it's an upward spin, I'll say S is plus half. So this is for the first electron. Let me write all the quantum number values for the second electron here. In that case also, since it's present in the first shell, N is 1. Since it's present in S subshell, L is 0. And for L is equal to 0, there is only one ml value possible, which is 0. And since I have shown the electron in an upward direction, the S value is plus half. So what you see here, you see 2 electrons in a way that they are having all the 4 quantum number values same. That's a violation of Pauli's exclusion principle. So that what you cannot do. So the only way to represent this second electron in an orbital will be that this electron will have an anti-clockwise spin. So how you are going to show it? You are showing will show the second electron facing the arrow facing downward, representing that the spin is anti-clockwise. And that's then the case then I'm going to write the spin quantum number value equal to -12. Now you can see here, the n value is same for both the electrons. The L value is same for both the electrons. The ML value is same for both the electrons. But the fourth quantum number value, which is spin, is different. So that it follows the Pauli's exclusion principle. So I can very easily now write the electronic configuration for helium as 1s2. 1s2. So that means the helium has maximum of 2 electrons, which are there in the 1s subshell and 1s orbital. For the lithium, the atomic number is 3. In that case, we have 3 electrons to be filled. So how I'm going to proceed? Again, I'm going to write down the electronic configuration. So the first box represents the first shell and the s subshell, and it has only 1 orbital, and an orbital can have a maximum of 2 electrons. So the first 2 electron is going to go in the 1s orbital. This is how we write it down. It's same as of helium. Same as of helium. Now where the third electron will go? Will the third electron will come into 1s orbital? The answer is no. You cannot have more than 2 electrons in an orbital. So where that third electron will go? That third electron, if you see here, will go into the 2s orbital. Will go into the 2s orbital. The reason? After 1s, this is the lowest energy orbital. This is the lowest energy orbital. So since there is only 1 orbital associated with 2s subshell, I'm going to draw just one box and write 2s here, and that 1 electron will come here. So I have accounted for all the 3 electrons in a lithium atom. So how I'm going to write down the electronic configuration? 1s2 and 2s1. So what does it represent? That there are 2 electrons in the 1s orbital and there is 1 electron in the 2s orbital. So this is the electronic configuration for lithium. So this is a complete electronic configuration. There is another way of writing this electronic configuration, which is called the condensed form of electronic configuration. For writing that, I'll take helium, which is the first noble gas in the periodic table. It has a completely filled shell. So I will write the electronic configuration of lithium as helium. So that means I have already counted for 1s2 and plus 2s1. So if you are writing electronic configuration in this form, this is called the condensed form of electronic configuration. It's a condensed form. So I have taken helium as the standard, helium as the reference. So helium has a completely filled 1s subshell. So that's what 1s2 and then is 2s1. So this is a condensed form of writing electronic configuration. This is particularly useful when you are writing the electronic configuration of heavy atoms. We'll take those examples in the class. So the next example which we are going to take is of nitrogen, and where we are going to use the third principle, which is the Hund's rule. Remember what I said, in a degenerate orbital, electron pairing will not take place until each orbital is singly filled. So what does that mean? So we are going to take that with an example of nitrogen here. So as you can see as a subscript, it's a 7 written here. So the atomic number of nitrogen is 7. So that means there are 7 electrons in nitrogen. So when I'm writing the electronic configuration, so I'm again going to start it with the boxes. So there is only 1 orbital in the 1s subshell. There is only 1 orbital in the 2s subshell, and as far as the 3p subshell is concerned, I'll again take you back. For L is equal to 1, the subshell is p. The subshell is p, and for L is equal to 1, the ml values which are possible is -1, 0, and +1. So there are 3 different ml values. So that means in a p subshell, there are 3 different orbitals. Remember the orientation we talked about, the double dumbbell shape. So, in that case, to represent a 2p subshell, I am going to draw 3 boxes, and each boxes represents one p orbital. So, I can say this is 2px, this is 2py, and this is 2pz. So, I will simply write 2p here. So, this is 2s and this is 1s. So, there are 3 p orbitals in a p subshell. L is equal to 1 and the ml value -1, 0 and +1. So, now I have to arrange electrons into these orbitals. So, there are 7 electrons. So, the first 2 electrons will go into the 1s subshell. So, I am going to write 1s2. Okay. The third electron will go into the 2s subshell, and so do the fourth electron. So, the 4 electrons are into 1s2, 2 electrons are in 1s subshell, 2 electrons are into the 2s subshell. So, that leaves me 3 electrons, and those 3 electrons will go into the 2p subshell. And remember, how many electrons, the maximum number of electron a 2p subshell can have is 2 times the number of orbitals. So, there are 3 orbitals. So, 2 times 3 is 6. So, I can arrange 6 electrons into these 3 orbitals. But how many I have? I have only 3. So, how do I arrange it? One way of arranging is, and all is, suppose I will put 2 electrons here and the third electron in this one. So, 4 plus 3 is 7, done. Now, let us see which rule it violates. Now, all these 3 orbitals 2px, 2py and 2pz are degenerate. They have the same energy, and what I have done here, I have done an electron pairing. So, I have done electron pairing in a degenerate set of orbitals. Is this right? The answer is no. It violates the Hund's rule. The Hund's rule states that you cannot have pairing till each set of degenerate orbitals are singly filled. So, in that case, the only way of arranging electrons into these 3 sets of degenerate orbital is where I put single electron in 3 orbitals. So, this represents the electronic configuration of nitrogen. So, I can simply write 1s2, 2s2 and 2p3. So, I again repeat, this is according to the Hund's rule. When I am comparing 1s with 2s, these are non-degenerate orbitals. They are not of same energy. 1s is of lower energy than 2s. When I am comparing 2s with 2p, these are non-degenerate orbitals because 2s is of lower energy than 2p. But when I am comparing the orbital in the 2p subshell, which is 2px, 2py and 2pz, they have the same energy. They are degenerate. So, they need to have single electrons. So, that is crucial. So, I will jump further to calcium, which is a metal in the second group. So, it has an atomic number of 20. That means it has 20 electrons in it. Let us see how the distribution will be. So, I will be drawing small boxes so that to accommodate all the boxes in this space. So, you have 1s orbital, then you have a 2s orbital, then you have 3 p orbitals. So, it is 2p. The next is a 3s orbital. Let us jump to a little bit further, to a little bit heavier atom than compared to nitrogen. It is calcium. This is the second group in the, it's an element which is in the second group of the periodic table. So, it has an atomic number of 20. So, that means it has 20 electrons. So, how those 20 electrons will be arranged? So, as we have seen earlier, it is very easy. There will be 2 electrons in the 1s orbital. There will be 2 electrons in the 2s orbital. There will be, how many electrons can be in the 2p subshell? There are 3 orbitals. So, that means a maximum of 6 electrons in a 2p subshell. So, you have 6 electrons here. So it's 1s2, 2s2 and 2p6. So I have accounted for 10 electrons. The next 2 electron will go into a 3s orbital, and then the next 6 electrons will go into the 3p subshell. So you have 12 plus 6 is 18. Now let's see where the 19th electron go. So 1s, 2s, 2p and 3s. 3p, after 3p what you're getting? You're getting a 4s subshell. You're not getting 3d, so mind it here. So it's a 4s. So the 19th electron will come into a 4s orbital, and so do the 20th electron. So the electronic configuration of calcium becomes 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2.